Welcome to the second lecture on advanced control systems. In this lecture, we are going to learn about the necessary and sufficient conditions for arbitrary pole placement. If you remember, in the previous lecture, we talked about control system design using state feedback. This is also and in this we actually arbitrarily placed the closed loop poles of the plant that we were trying to control. So in effect, what were we doing was arbitrary pole placement, right? So this control system design using state feedback is also called arbitrary pole placement. Now today we are going to go a little deeper into the topic and see when can we do this. Can we do this for all kinds of systems? What are the limitations of this method? What kind of flexibility it gives us in terms of controlling the plant, and other topics which are related to this. So before continuing, we'll take one more example to see what we did on the last term. So suppose we have a system which is unstable basically. So you have an unstable plant and you want to stabilize it, right? Using this control law which we saw in the last term, which was U is equal to minus kx. So an example of an unstable plant could be something, say we are talking about a second order system so that the calculations are easier. So something which has poles on the right half plane like this. If you have poles on the right half plane, this is the S plane, right? So this is the imaginary axis, this is the real axis. If you have poles here, your response to step input would be something like this. It'll be a oscillating response with continuously increasing oscillations. So this is the response of the system, and you want to stabilize it using the method that we studied on the last term. So suppose this is the location of the poles, and you want now to change the location to say this. You want to bring the poles to the left half plane, and you want to bring both the poles to the same location, right? So these are two crosses. So I'm going to change the pole location, bring both the poles to the same location here, right? And I want to do this using the control law that we discussed on the last term. So an example of this kind of system is, say, for example, something that has a transfer function like this, 5 divided by s square minus 2s plus 2. So if you look at the denominator, you'll see that when the characteristic equation is s square minus 2s plus 2 equal to 0. So this is the equation for the plant, right? And when you equate this to 0 and try to see what is the value of s, that is where are the poles located, you'll get s is equal to 1 plus minus j. So it's an example of an unstable system which will have oscillatory unstable response to a step input. Now I want to change this using the feedback law that we discussed in the last turn, and say I would like my poles to be here, both the poles to be here. So I would like my modified transfer function, right? Modified transfer function, right? After I apply the closed loop control, after I apply the state feedback control, the modified transfer function, or let me say the modified characteristic equation, right? Because we're trying to change the characteristic equation. So the modified characteristic equation should be such that you get two poles at -1. So the modified characteristic equation will be s plus 1 whole square equal to 0, which is s square plus 2s plus 1 equal to 0. So in effect, what we are trying to say is that this is your characteristic equation equal to 0, and you want to change, this is an unstable system, and you want to change it to this using the state feedback law that we studied on the last time. So we can do it very easily by just comparing the coefficients and finding the values of the gains. But let us look at one more method to do the same thing, right? So if you look at this plant that you have, GS is equal to 5 divided by s square minus 2s plus 2. Let us write down the state space representation for this. We can straight away write down the state space representation in controllable canonical form by inspecting this. So in the numerator, this is a second order system. So you have 0, 1 in the numerator, and the denominator you have A0, this is your A0 minus A0 minus A1. So in the reverse order you're writing. So this will be -2 minus 2. The B matrix for this system would be 0, 1. And the C matrix for this system is, if you remember, B0, B1, that is the numerator terms. So this 5 is a B0. There is no S term, that is B1 is 0. There is no S squared term, so B2 is 0. So your C matrix is 5, 0. Now this is the state space representation of this system. And when you apply for this system, when you apply the control law, U is equal to minus kx, right? Which will be minus k1, k2, x. What is going to happen is that your modified representation would become x dot is equal to a minus bk x. We saw it on the last term. So the A matrix for your new system is A minus bk, right? So your A was 0, 1, minus 2, 2. Your A minus bk would be where B is given by this. So your A minus bk would be 0, 1, minus 2 minus k1, minus 2 minus k2. And the characteristic equation for this new system, x dot is equal to a minus bk x, would be given by the determinant of si minus a minus bk, right? So we already know this. We know that the transfer function, for conversion from transfer function representation to state space from state space to transfer function, we know that if something has state space representation given by x dot is equal to ax plus bu, y is equal to cx, then the transfer function of this is si minus a inverse c in b plus of it also has a d term, so plus d. We already know that this is the transfer function. So in the transfer function, you can see that the denominator of the transfer function would be the determinant of Si minus A, right? So for this system, x dot is equal to A minus B kx. We are not converting it completely into the transfer function representation for this system. We're just saying that the characteristic equation for this system would be determinant Si minus A minus Bk equal to 0, right? So this is the determinant for the new. This is the characteristic equation for the new system that we have, which is obtained after we apply state feedback law to the original system. Now look at A minus Bk and try to find out the determinant, right? So it's not very difficult. Si minus A minus Bk would be, so what we're trying to look at is Si minus A minus Bk. So this is going to be S plus 2 plus K2 minus 1, 2 plus K1. And the determinant of this thing, right? So the determinant of this thing here is going to be S into S plus 2 plus K2 plus 2 plus K1, which is equal to S square okay. So this is Si minus A. So this is okay. S plus, okay, I did something wrong here. Yeah, so this is not minus, this is minus 2 minus K1. This is 2 minus K2. So this is 2 minus K2, right? So this is 2 minus K2. So this will be minus here, minus here. So this is again minus here, right? So this is S into S minus 2 plus K2 plus 2 plus K1, right? So this is going to be S square plus K2 minus 2 into S plus K1 plus 2. So the new system has, your new system has this characteristic equation, right? And your desired characteristic equation, if you look at what you wanted, was S square plus 2S plus 1. So this has to be equal to the desired characteristic equation. So this has to be equated to S square plus 2S plus 1. Now if you equate these two, you'll see that K2 minus 2 has to be equal to 2, and K1 plus 2 has to be equal to 1, which means that K1 is minus 1 and K2 is 4. So a feedback law U is equal to minus Kx, where K is equal to minus 1, 4 would move the poles to the left half plane at minus 1 comma minus 1, right? So this is another way that we have seen that we can compare the equations directly. We can compare the equations directly, and we can find out the values for K1 and K2. This is a more cumbersome procedure. The procedure that we saw on the last turn was easier, was simpler, and we can verify whether we're getting the same results, right? So on the last turn, you saw that if you have an equation, a characteristic equation which is given by S square plus plus A1S plus A0 equal to 0. This is your actual equation, actual characteristic equation for the plant. equation for the plant, and then you have a desired characteristic equation for the plant, S square plus alpha 1 S plus alpha 0 equal to 0. So this is desired. Then you can find out your K matrix by just subtracting the two. So your K1 would be alpha 0 minus A0, and your K2 would be alpha 1 minus A1, right? This is when your plant is actually in the controllable canonical form, right? So from this you can see that your actual characteristic equation was S square minus 2S plus 2 equal to 0, and your desired characteristic equation was S square plus 2S plus 1 equal to 0, and from this you can see that your K1 is equal to 1 minus 2, so that is 1 minus 2, that is equal to minus 1, and your K2 equal to K2 is equal to 2 minus minus 2, so 2 minus minus 2, that is equal to 4. So your K1, K2, or your K matrix is equal to minus 1, 4. And this is the result that you got here, right? So this is the result that you got here. You got your K1 as minus 1 and K2 as 4. So this is another way of solving the same problem. And in this we saw that we can directly compare the two in characteristic. We can just add the state feedback law to the state space representation, find out the characteristic equation, desired characteristic equation, and then compare the two equations to find out the values of K1 and K2. It is easy to do this for a second order system, but if the order of the system is higher, then it becomes difficult. So now we have seen that we can place the closed loop poles arbitrarily for a plant, and in this case we have stabilized the plant whose initial pole locations were such that it was an unstable system to a location such that the system becomes critically damped and stable. Now the next question that arises is, the obvious question that arises is, can we do it for all systems, right? Can we do this for all systems, right? And what happens, so what are the necessary and sufficient conditions for arbitrary pole placement, right? So we have already seen that if our system is in controllable canonical form, then we can do arbitrary pole placement. Why is this? Because in the controllable canonical form, the characteristic equation is very clearly present in the denominator, right? So 0, 0, 1, 0, 1, 0, this minus A0, minus A1, minus A2. So you just have to change these coefficients using the state feedback law. When you apply A minus BK, this becomes 0, 1, 0, minus A0 minus K1 minus A1 minus K2